So welcome back, everybody. Where I left off yesterday, let me grab my last sheet. So this was the last thing that I wrote yesterday, which was to put a complex number into this polar form using polar coordinates, if you like. So we wrote the complex number like this. And defining this symbol e to the I theta to be cosine theta plus I sine theta, I was able to rewrite this polar form into this exponential form thing, which turns out this is going to be the thing actually of interest to me. So in one way, you can kind of think about this as cheating to define this formula in this way, because of course, you already have something that you think about when you see e to the I theta. When you see e raised to anything, you're already thinking about this in terms of the exponential function. So, just defining this symbol e to the I theta to mean this might be viewed as a little bit of cheating. So I'm going to go ahead and spill the beans on exactly where this comes from if you haven't seen this before. So actually, we don't need to cheat and define this to be this quantity. E to the I theta is actually equal to cosine theta plus I sine theta. This is called Euler's formula, or as I said, a very specific special case that I'll talk about in a second is called Euler's formula, which you've probably seen. And so how can I actually see that this is true? So the easiest way kind of to see how this works is to note that if we're just speaking purely formally, so what I mean by that is I don't care about specific questions of convergence and things like that, so I'm not going to get into anything like that. But just formally, right, if I consider right, if I consider the exponential function, right, e to the x, then I know that there's a power series representative of this thing. So there's power series representation for this function, and I could obtain that via, whatever your favorite method is. If you want to write this as its Taylor series, this series is the following. So it's the sum from n equals 0 to infinity of x to the n over n factorial. Okay, now of course, since the series is actually equal to e to the x, there's nothing wrong with this power series. This power series converges for any value of x, so I don't have to worry about anything like that. But I don't even want to talk about issues of convergence, so I'm just going to totally ignore it. So we're going to treat this purely formally, meaning that whatever I plug in here to x I'm just going to treat it purely algebraically. I'm just going to symbol push. Okay, so of course, this is defined for a real number x. All right, so this is a real variable here. But what if I plug in, say, I theta here, right? So I do e to the I theta plugged in here, and I get this power series that looks like this. I have I theta raised to the n over n factorial, okay? So then what is the idea here? Well, I'm going to have, if I write, a few terms of this thing, right? So maybe if I write a few terms of this power series, all right, so this is like 1. So when n is equal to 0, anything to the 0 is considered 1. 0 factorial is defined to be 1 because that makes more sense. So the 0th term here is just 1. The first term is plus x to the first over 1 factorial, which is just 1, plus x squared over 2 factorial, plus x cubed over 3 factorial, and so on, right? So that's what this thing looks like. So if I'm just formally plugging in I theta here, this would be 1 again, since the 0 term is always going to be 1, plus this is going to be I theta to the first over 1 factorial, plus I theta to the second over 2 factorial, and so on. Okay, I'm actually going to write out a few more terms here, and you'll see why in a second. So maybe I'll write one more term, and then I'll be happy. Okay. All right. All right, so this is what I'm doing. Now again, forget that, you might not really understand what rules are at play when you plug in some complex value into a real function of a real variable. But again, we're just doing this purely formally, and we're going to just do some symbol pushing here. So what do I need to do in order to make this maybe tolerable to deal with? So to make this tolerable to deal with, I will note that, of course, I itself, right, is the imaginary unit, but I want to compute powers of I. So I squared, right, what is I squared? Well, I squared is -1, so that's nice. Okay, what is I cubed? Well, I cubed is really I squared times I, right? But I squared is -1, so I cubed is I squared times I, which is minus I, right? And so what's I to the fourth? Well, I to the fourth is I squared squared, so that's -1 squared, or 1. So what's I to the fifth? Maybe I've run out of room here. I'll do it up here. What's I to the fifth? Well, I to the fifth is I to the fourth times I, but I to the fourth is 1, so this is just I, and we repeat. Okay, and so these powers of I cycle, and when they cycle, they go like I, then they go to -1, and then minus I, and then 1, and then back to I, and it repeats like that over and over and over again. Okay, so knowing that, I can simplify this power series a little bit. I've written out like this. So this is, and we're actually going to do this argument fully later on in in the course, but I just couldn't leave you hanging like this by cheating and just defining it that way. So this is 1 plus I times theta over 1 factorial. Plus I squared is -1, so this is actually minus theta squared over 2 factorial. And let me give myself some demarcation here. Plus I cubed is minus I, so this is actually another minus I theta cubed over 3 factorial. Plus this is going to be I to the fourth, but I to the fourth is just 1, so this is plus theta to the fourth over 4 factorial. And I to the fifth is just I, so this is just plus I theta to the fifth over 5 factorial, and so on. Okay, and so let me rewrite this. Okay, so let me rewrite this so that I can actually make sense of it. So e to the I theta, if I write this power series out term by term, this is 1 plus I theta over 1 factorial minus theta squared over 2 factorial minus I times theta cubed over 3 factorial plus theta to the fourth over 4 factorial plus I times theta to the fifth over 5 factorial, and so on. Okay, and now what I want to do is separate these terms. So notice that the i's don't show up on the even powered terms. So the 0th power, the 2nd power, the 4th power, the 6th power, the i's don't show up. That's not mystical or anything. That is simply because for the even powers of I, you don't get an I showing up. So the 2nd power of I is -1, the 4th power is 1, and it just flips back and forth between 1 and -1. Okay. All right. So then, how does this go? Well, the idea here is to note, if I split the even terms, the ones that don't involve I get this thing. I'm going to regroup that. I'm going to group that as 1 minus theta squared over 2 factorial plus theta to the fourth over 4 factorial Turns out that's going to be a minus. You can check that because I to the 6 is minus 1. So this is minus theta to the 6 over 6 factorial, and so on. Okay. But what is left in the odd powers? So in the odd powers, right here, what do I get? Well, in each of these I have an I. So if I pull out that I, if I factor out that I, again, don't pay attention to the fact that I'm factoring out something that's multiplying an infinite sum. We won't talk about that at the moment. It's perfectly fine what I'm doing there, but like I said, we'll just ignore that. And so if I pull this I out here, what do I have left? I have theta, right, over 1 factorial, minus theta cubed over 3 factorial, plus theta to the 5th over 5 factorial. And if we kept going, you'd see that this is minus theta to the 7th over 7 factorial. So the deal is this is actually the power series representation for cosine theta. Okay, this is the power series representation. Of course, this keeps going for sine theta. And so just purely formally speaking, using power series, e to the I theta is cosine theta plus I sine theta. Okay. So this is a derivation of Euler's formula in this way. Okay, this justifies why we are able to represent a complex number in this way. Okay, all right. So again, we'll talk a little bit more about this later, but that's me spilling the beans a little bit. Okay, so then going back, we have complex number z in polar form. I've written it as r cosine theta plus I sine theta, but I can use this fact that this is this quantity here I just showed via Euler's formula is e to the I theta, so this is r e to the I theta. Okay, so this is polar form, this is exponential form, they're really the same thing here, and this is going to be very, very important for us. Okay. The reason why this is going to be so important is because this allows us to do a lot of algebra in a really, really nice way. So because these exponents can get large, sometimes actually writing them in an exponent's a little tricky because it's so long that it can become unclear in a long equation what's actually in the exponent and what's down below. A lot of times you'll see instead of e to the whatever written here, you'll have the expression r exp for exponential of whatever. So I theta in this case. All right, so of course if it's just I theta, that's not a problem, but when you have a very long expression in the exponent, a lot of times it's a lot more convenient to write this instead, so that you're writing it all in the same line. Okay, and so let's do a quick example. Yesterday we found we talked about the argument for the complex number minus 1 minus I. So let's let z be minus 1 minus I. I want to put this in exponential form. So how do I do that? How do I put this in exponential form? Well, so if I want to put this in exponential form, first of all, r is the modulus of z. So what's the modulus of z here? So this is square root of minus 1 squared plus minus 1 squared. All right, so this is square root of 2. Okay, so there's my modulus. The argument, right, we found for this, so arg z from last time was found to be minus 3 pi over 4. Right. Okay, and so with these two pieces, I can say that z is square root of 2 e to the minus 3 pi over 4i. Okay, or written in this form again, because you see, even for something simple like this, you know, you end up with something that can be, you can get pretty small when you're writing here. You can say this is square root of 2 times the exponential function applied to minus 3 pi over 4i. Okay, so this is me putting it in exponential form. Okay. Of course, you might say, well, you use the principal value of the argument here. So since this polar form actually doesn't have a unique representation, aren't there technically infinitely many ways of expressing this in exponential form? And the answer is yes. So this is just one way of doing it, but this is not the only way. So if I give you this, if I give you z is minus 1 minus I, and I ask for exponential form, this is not the only answer you could give to be correct. In fact, how do I actually write out the full answer? Well, instead of using principal argument, I would just use arg z instead, right? So arg z, one way of writing it, of course, is minus 3 pi over 4 plus 2 n pi, right, for n, an integer. Okay. All right, and so if I use this instead, then my completely general exponential form would be root 2 times e to the I, we'll say minus 3 pi over 4 plus 2n pi times I for n in the integers. Okay. So this is the completely general form. The benefit here is that now you can say that any exponential form of this complex number has to be one of these, right? So it has to be one of these for some choice of n. Okay. So this is nice for taking care of, for handling all bases, because technically, right, if you're computing with a thing like this, while this is an exponential form for that, it's not the only one that can show up. This is something you have to keep track of. It can be a little bit annoying, but once you get a hang of it, thankfully, it's something that you're going to be able to quickly dispatch as a concern for the most part, pretty quickly. Okay, so of course, directly from Euler's formula, you notice a couple of things. So for instance, the most famous thing that you might notice is e to the I pi, right? E to the I pi is cosine of pi plus I sine of pi. Sine of pi is 0, so this is minus 1 plus I times 0. So this is just minus 1, right, which yields the special case of Euler's formula that is typically called Euler's formula itself. Everyone loves this, right? It's relating e, I, pi, 1, and 0, right? 5 very important constants in math related by this formula, but this is exactly where this comes from. Here in a second, I'm going to mention you can just see this in the plane if you actually think about what is going on when you write a complex number in polar form. Okay, so of course there's some other specific values here that come up often. So e to the minus say pi over 2 I. This is, what is this? Well, this is cosine of minus pi over 2 plus I sine of minus pi over 2. Okay. Cosine minus pi over 2, well, cosine's even, so this is the same as cosine pi over 2, that's 0. And sine of minus pi over 2 is minus 1, so this is minus I. Okay. So minus I has e to the minus pi over 2i as its exponential form. Okay, and of course one more that you could write up or notice. What about e to the, say, 2 pi I? So here's, this is cosine 2 pi plus I sine of 2 pi. Well, cosine 2 pi is 1, and sine 2 pi is 0. So this is 1 plus I times 0, so this is just 1. All right, so e to the 2 pi I is just a creative way of writing 1 here. Okay. All right. So one more nice way of thinking about exponential form, and then I'm going to show the practical reason why we're so interested in writing a complex number like this. Okay. So if I consider the following equation, so let z be a complex number such that z is equal to r e to the I theta, okay, where theta ranges between 0 and 2 pi. What does this equation describe? What does that equation describe? Well, this equation actually describes a circle of radius r centered at the origin. So, oh, that's bad. That's a pretty bad circle. Okay, but you can pretend that it's a good circle. So here's a circle of radius r centered at the origin. Right, and so this can be thought of as parametrically describing this curve in the following way, right? So theta beginning at 0, that's this point, right, on the positive x-axis. As theta varies from 0 to 2 pi, it goes around circle counterclockwise and back to its initial point when theta is 2 pi. Okay, so this is really a parametric description of a circle of radius r centered at the origin. Okay, of course, the circle of radius r itself has equation, right? Modulus of z is equal to r. That's this circle. Okay, but this is a parametric description of this circle. So this is parametric description of the circle modulus of z is equal to r. Okay. And it doesn't take us too much thinking to actually take this from a circle of radius r centered at the origin to a circle of radius r centered anywhere. So how do I come up with a parametric description for that? Well, the idea is, instead of dealing with the circle modulus of z is equal to r, if I'm dealing with the circle modulus of z minus z naught is equal to r, right, here's my generic circle centered at z naught of radius r. Maybe I'll get another piece of paper here. So let's say here's my complex number z naught. Here is a circle of radius r, right, centered at z naught. So here's my way of writing that equation using this notation that we talked about yesterday. So circle of radius r centered at z naught. So how do I parametrically describe this thing? Well, taking a cue from what we did earlier, this is actually just z is equal to z naught plus r e to the I theta, where theta goes between 0 and 2 pi. This is the parametric description of this circle. How does this work? How can you think about this? You have this initial vector specified by z naught. So there's your vector specified by z naught. This angle theta then is measured from the positive x-axis by, you think, oh, well, I have this parallel to the positive axis here, and I measure theta around the circle from that reference line. Okay, so again, it parameterizes in the same way. It is, you think about starting at this right point on the circle, right, and you're going counterclockwise around the circle, starting from that point. Okay. So that's how this works. So this gives a parametric description of description of the circle. Modulus of z minus z naught is equal to r. Okay. Again, this is kind of a nice way of expressing these things in exponential form. Okay. All right. And so we come to the actual main motivation for talking about exponential form, which is fact, and maybe I'll put stars here because this is very important. Exponential form makes much of the algebra of complex numbers significantly easier. Okay. So writing them in this way makes a lot of the computations that you're going to have to do and a lot of the basic algebra stuff that you're going to do so much easier to handle than rectangular form. Okay, so that's really the major benefit. Okay, and you're going to see that immediately. And so what's nice is actually I don't need to rely on this. I don't need to rely on this justification that I gave using power series. If you like, you can just pretend that we cheated and defined the symbol e to the I theta to be cosine theta plus I sine theta. And if we did that, then you'll note that we're going to be able to derive all of the usual properties of the exponential function anyway. Okay, and so one particular thing to note is the following. What happens if you multiply two exponential things that look like this? So e to the I theta sub 1 times e to the I theta sub 2. Well, if I'm just using that definition, right, and I'm not actually treating this as an exponential function, well, then this is cosine theta sub 1 plus I sine theta sub 1 times cosine theta sub 2 plus I sine theta sub 2. Okay. Multiplying this out, what do I get? Well, so the real part is going to be cosine theta 1 times cosine theta 2. I sine theta 1 times I sine theta 2. I get I squared, which is minus 1. So this is minus sine theta 1 times sine theta 2. Okay, plus I times the other terms, so the mixed terms here. So I'm going to have I sine theta 1 times cosine theta 2, so that's sine theta 1 times cosine theta 2, plus sine theta 2 times cosine theta 1. Okay. And now, if you look closely and you think to yourself real hard, you might say, wait, I've seen these expressions before. And if you remember all of your nice trig identities, right, from high school, you'll notice that these are two of them. All right, so these are two of those trig identities. Which ones are they? You can type it in chat if you realize which trig identities we have sitting in here in front of us. This is the cosine angle sum, right? So this is cosine of theta sub 1 plus theta sub 2 plus I times sine of theta sub 1 plus theta sub 2. So these are angle sum formulas for sine and cosine. So you're forgiven if you don't have those memorized off the top of your head, but this is exactly where they come from. Well, I should I kind of spoiled the fun there. So the way that I remember these formulas is exactly from this expression. Okay, but okay, so of course, what does this mean once we have them written as angle sum here? This means that this is e to the I times theta sub 1 plus theta sub 2. Right? So you might look at this and say this is a really like long-winded, convoluted way of saying that this exponential, this symbol that you're writing that looks like an exponential thing, it actually behaves in the exact same way that exponential things do. But we have to do that if we defined it this way, right? Now, if we use the if we use the power series proof of it, we can skip all that and say this behaves just like e to the x, and so formally, or just doing these sorts of multiplications or raising to powers works out nicely. And so the other thing is that if we know that this is actually the exponential function, then this is actually a way of deriving these identities. And we're going to do that for another identity, for two other trig identities later. But yeah, so if we actually take for granted that this e to the I theta is actually an exponential thing, then the fact that e to the I theta 1 times e to the I theta 2 is equal to e to the I theta 1 plus theta 2, that actually can be used to set these two, the real and imaginary parts, equal to each other, to show those trig identities. This is actually one of the easier ways to prove those trig identities. Some trig identities can actually be kind of nasty to prove, but using complex, the algebraic complex numbers and this polar form or exponential form, it is actually really easy to to prove some of these formulas. So like I said, I'll show you an example of that later. Okay, so why is this nice? Well, this tells us that if we multiply two complex numbers in polar form, then what we get are complex numbers in polar form, right? So if we have a complex number z1 that is in polar form, so r1e to the I theta sub 1, and z sub 2 is r sub 2 e to the I theta sub 2, right? If those are our two complex numbers in question, if we multiply those, right, then dealing with this is really easy. This is r sub 1 e to the I theta sub 1 times r sub 2 e to the I theta sub 2. Of course, I can rearrange the multiplications here, so this is really just r1 r2 times e to the, now that those two are going to be multiplied, it's e to the I theta sub 1 plus theta sub 2. Okay. And so multiplying two complex numbers in polar form gives you a very easy description of their product in polar form. Similarly, right, dividing, right, forming a quotient of two complex numbers in polar form also gives a really nice description in terms of exponential form. So this is just r sub 1 over r sub 2 times e to the I theta sub 1 minus theta sub 2. Right? So no need for additional algebraic trickery there. This just has a very nice description in exponential form. Okay. All right. And so there's two algebraic operations that are made a lot easier in this way. What else? Well, powers, right? Powers are nice here. So if I have z to the n, well, this is r e to the I theta raised to the n. Right? So this is r to the n times e to the I theta to the n. That's just it multiplied by itself n times. So iterating that product formula from above, this is e to the I n theta. Okay. Now I can be cautious here and actually prove this using induction by starting just with raising this to the second power and then inductively defining this. This is also true for negative n, right? So n here can be an integer. N can be -1. It can be -5. Okay, I'm not actually going to go through the full proof of that, but if you want to see how that's justified, you can look in your textbook to see how that is carefully justified that this can be done using induction. Okay, so you can do this in using induction here. Okay, so then how can I use this to my benefit in actually doing some computations here? So let's start out by considering, say, the following question. I want to write the complex number square root of 3 plus I to the 7th in rectangular form. Okay. So how do I do that? Well, note that if I wanted to do this by like brute force, this would involve me doing some binomial theorem thing, right? Expanding this binomial and using the binomial theorem to figure out that this is taking the shortcut, right? I'd use the binomial theorem to figure out what each of the coefficients, or each of the coefficients in that triangle were, in that layer, and then I would write that thing out and I would try to simplify it the best I could from there. Or I can use exponential form and make this really, really easy. Okay, so first step is to put this into exponential form. So I'm looking at my number z, which is square root of 3 plus I. So to put this in exponential form, if I want to write this as some r e to the I theta, right, how do I do that? Well, first of all, finding r is not too bad. R is just the modulus of z. So I can quickly write that out. This is square root of root 3 squared plus 1 squared. So this is square root of 4, which is 2. Okay. All right. Okay, so r is 2. How do I find theta? Well, again, from polar form, one of the ways of thinking about theta is that tan theta is y over x here, right? Where the y over x, remember, they come from the fact that z is x plus iy, right? So y is the imaginary part, x is the real part. So the tangent of theta is equal to imaginary over real part. So for this z, that is 1 over root 3. Okay. All right. And so this is tan theta is 1 over root 3. Let's think trig for a second. Tan theta is 1 over root 3. Tan is sine over cosine. All right. Well, when's tan theta 1 over root 3? This is when... So, of course, it's a trig equation. Infinitely many values here, right? Which is the principal value that I'm going to pick here? Right, so the principal value I'm going to pick is pi over 6. Right? Again, it's a trig equation, so this is not the unique choice here, but any choice will do. Why? Because rectangular form doesn't have this ambiguity, so any choice I make here has to give me the same answer in rectangular form. Okay. And so we have successfully found the polar form for z. And so I have my question is to write square root of 3 plus I to the 7th in rectangular form. So making this into, or using its polar form rather, this is 2 times e to the I times pi over 6 to the 7th. So this is 2 to the 7th times e to the I times 7 pi over 6. Okay. So how do I nicely deal with this? That's kind of a convenient way of dealing with this. Well, I actually notice that I can treat this as a multiple of the thing that I started with here. So for instance, right, if I peel off one of these 2's, I would have 2 to the 6, right, times 2, times e to the, I'm going to peel off a pi over 6 here, so that I'm just going to have a 6 pi over 6, or just pi, left over there. So this is 2 to the 6 times e to the I pi times 2e to the I pi over 6. Now, why did I do that? It's because I already know the rectangular form for this. This is square root of 3 plus I. That's the thing I started with, right? And so what I have left here is pretty easy to handle. E to the I pi is minus 1, and 2 to the 6 is, so 2 to the 5 is 32, so 2 to the 6 is 64, right? So this is minus 64 coming from this, times 2e to the I pi over 6 is square root of 3 plus I. And so in rectangular form, this is minus 64 square root of 3 minus 64 I. Okay. Okay. So if you have questions about that, feel free to let me know in the chat. But we tried to do our best to avoid doing additional computations here. We just used what we had and some simple values that we knew of e to the I whatever, right? So e to the I pi here is one of our simple values. Okay. And so if we actually focus on something that we did here, right? So for instance, whenever we had this expression, well, just iteratively multiplying e to the I pi by itself n times and using our formula for the product means that I get what? Well, I can see that this behaves in exactly the way the exponential function usually behaves with respect to this. So this is e to the I n theta. And this is something that I can do for any integer power n here. Okay. And so, what do I note? Well, this tells me something, first of all, right off the bat. So what this tells me is that if I revert to polar form, this is cosine theta plus I sine theta to the n. And that is equal to, in polar form, what is this? Now the n is actually multiplying the argument here, right? So this is cosine of n theta plus I sine of n theta. That's a pretty cool formula, but it's basically trivial if you know this, right? But it turns out that this is the case even, right, if you forget this exponential business, this is true. And of course, the easiest way to see it is from writing it in exponential form. But this is true, and this is called Demarvor's formula. Okay. Just a quick aside here. Demarvor actually has a pretty funny story. So Demarvor had letters of recommendation from both Newton and Leibniz. Okay. So letters of recommendation from both Newton and Leibniz. and still did not manage to get a professional math teaching job, and had to rely on odd jobs as a tutor and answering questions for gamblers. So, that's kind of a, he's like a nexus of unluckiness, right? It would be a pretty sad feeling to have letters of recommendation from Newton and Leibniz, and that's still not good enough. It'd be pretty rough. Anyway, so this is Demarvor's formula. So I'm going to use this actually to show this is a tricky proof of some previous trig facts that you've learned before. So for instance, what I want to do is note that Demarvor's formula with n equals 2 is just the statement that the cosine theta plus I sine theta squared is equal to cosine of 2 theta plus I sine of 2 theta. Okay. And so this is Demarvor's formula with n equals 2, but if we actually just expand this on our own real quickly, so let's do that. So if I take this and I expand it on its own here, this is so this would be cosine theta times cosine theta. So this is cosine squared theta. The squared terms here would be I sine theta times I sine theta, so that's minus sine squared theta. So that would be the real part of this expression. Plus I sine theta cosine theta plus I sine theta cosine theta. So this would be plus I times 2 sine theta cosine theta. What happens if I equate the real parts and the imaginary parts? Right, so if I equate the real parts, I get cosine of 2 theta is cosine squared theta minus sine squared theta. And sine of 2 theta is 2 sine theta cosine theta. Hey, this is our favorite double angle formulas, right, for cosine and sine. Okay. So no need for any kind of more obscure proof. This does it pretty quickly, right? In one step, takes care of both of those proofs. Okay. Yeah. So this is just a nice way, and it's not just true for these trig identities you've seen. So angle sum formulas for cosine and sine, double angle formulas for sine and cosine. In fact, I encourage you, think up some other, dig up some trig identities and see if you can use complex algebra to actually come up with some easy proofs of those things. Okay, so that's another nice application of these of this this stuff that we're doing. Okay, so we used exponential and polar form to handle products, powers, and quotients nicely. It's just a convenient way of dealing with those things. So now the question is to consider arguments of those quantities. So I want to talk about arguments of products and quotients. And this is key for what we're going to talk about immediately after, which is roots of complex numbers. Okay, which is definitely kind of a stark difference in what you get when you're doing algebra with real numbers. It's one of the big differences is that complex numbers have all of their roots, and we'll see what that means in a little bit. But first of all, if I want to go back for a second to relabel, so if z sub 1 is r sub 1 e to the I theta sub 1, and z sub 2 is r sub 2 e to the I theta sub 2. If I don't write this out and I just instead skip and start writing z sub 1 and z sub 2, then you can just assume that this is the underlying notation that's going on in the background. So then if I look at the expression, which is their product, z sub 1 times z sub 2, then by what we said previously, this is I multiply r sub 1 and r sub 2, and this is multiplied by e to the I theta sub 1 plus theta sub 2. Okay, so this formula directly from exponential form allows me to immediately say with, so I'm not going to say too much more about it right now, but it's going to allow me to immediately say, well, no, I can talk about it. This allows me to compute the argument. Remember, when I write lowercase arg, this is the general form. So this is including all possible values, right? So this is thought of as a set of numbers. It's not just one particular value here. So the argument of the product z1 times z2 is the argument of z sub 1 plus the argument of z sub 2. Now, very important that I'm stressing that this is lowercase arg and not uppercase principal value, because this equation is not always true for the case when you're dealing with principal arg instead. And so actually the first example I do here is going to show exactly that is not true in that case. But it's true when you're talking about all of the values here. Okay, and so to see that, like I said at first I wouldn't go through it, but it's kind of a tradition for me to at first balk at going over the details, and then I end up doing it anyway. So let's let theta 1 and theta 2 be some values in argument of z1 and z2 respectively. Okay. Then if this so if this statement is going to be true, then what must be true is that theta 1 plus theta 2 has to be a value in the argument of the product. So then theta 1 plus theta 2 is a value in the argument of the product z sub 1 times z sub 2. Okay. All right. And so what is it that I'm really saying here? Like, what is the importance of this starred statement? The idea is that if I am given any two of these, right, then I could find the third via this relationship. So there would be a way of finding the third. Okay. And so if I am given these two, finding a value in the third is easy. It's just the sum. How would I do that if I was given, say, these two? So product and argument of, say, z sub 1 here. Right. So then what that means is that if I am looking at arg of z sub 1 times z sub 2, this is going to be some theta sub 1 plus theta sub 2 plus some multiple, some integer multiple of 2 pi. Okay. And of course the argument of z sub 1 is going to be theta sub 1 plus 2 to times k pi, right? For k some integer. All right. But then I can actually notice that there's some algebra trickery to be done here. where I can say, well, really, theta sub 1 plus theta sub 2, right, plus 2 n pi can be rewritten as theta sub 1 plus 2k pi plus theta sub 2 plus 2 times n minus k pi. Okay. Well, just check to make sure this algebra is fine here. So I'm going to have a minus 2k pi that gets rid of that, and I'm going to be left with theta sub 1 plus theta sub 2 plus 2n pi, which is what I started with here. Okay, so doing this rewriting, well, then note that that is in the argument of z sub 2. And this works, right? So this would be our solution in that case. So this works, right? Now, what is it that I'm doing? It can be a little bit confusing here. So what I'm saying is that in this equation, right, if I'm given any two of these things, I could find the other without too much trouble. So the easiest thing to assume is that I'm given argz1 and argz2. If I'm given two values there, finding a value of argz1 times z2 is easy. It's just the sum of those things. But if I'm given, say, if I'm given the argument of the product and argument of one of these things, then it's actually not too hard to find a value in the argument of the other. And of course, I can use a symmetric argument for if I was given something in argz2 instead. Okay. And so the main thing to note is that this is not always true. So not always true if I replace arg with the principal argument. Okay. So this statement as written is always true, but not always true if I replace this with principal argument. So now I want to do that. I want to illustrate why that is. So let's do a quick example. So if I let z sub 1 be minus 1 and let z sub 2 be I, okay, then the principal value, right, the principal argument of z sub 1 times z sub 2, this is principal argument of minus I, right, minus 1 times I, so it's principal argument of minus I. Minus I, what is that argument? Let's think for a second, right? It can be helpful to do this. Where's minus I in the complex plane? Oh, it's here, right? Here's minus I. So what is the principal argument here? It's minus pi over 2. Right, so this is minus pi over 2. Okay. All right, but what is principal argument of z sub 1? So that's the principal argument of 1, or sorry, minus 1. But what is the argument of minus 1? Well, minus 1 is here, right? What is that? So remember, if we're in a situation where, for principal argument, where we could pick pi or minus pi, we pick pi. Okay, that's how this is defined. Otherwise, it would be ambiguous there at those points. So this is pi. Okay, and the principal argument of z sub 2. Z sub 2 is I, so here's I. So principal argument is pi over 2. Right, so this is pi over 2. Okay, so argument of z sub 1 plus arg z sub 2 is actually pi plus pi over 2, which is 3 pi over 2. So these are not equal. Right? What is wrong with this? Right? What is happening? Note, if we use these values in arg instead, well, I note that if I look at arg of, so principal argument of z sub 1 times z sub 2, if I take that and I add 2 pi to it, I get minus pi over 2 plus 2 pi. Of course, I could have added other multiples of 2 pi, but this is the one that's going to work and show that these are actually equal. So minus pi over 2 plus 2 pi. Hey, it works in that case, right? So this is showing you why you have to use lowercase arg here, right? Instead of the principal value. Okay. All right. So that's a nice fact. I'm actually going to rewrite that. Maybe I'll get another sheet of paper, so I'll rewrite that. So here I'm going to rewrite the fact that arg of product is actually the sum of the arguments. If I consider the argument of quotient, what do you think this is? Well, treating this using the product form, this is arg z1 plus arg of z2 inverse. Okay. But how do I invert something in exponential form? So here's a little aside. Right? If I have z, and I have z in exponential form, what is z inverse in exponential form? You might say, wait, that is kind of curious that you didn't go over that, right? You didn't specifically mention a formula for that. But I did, right? Because this is actually just 1 over z, right? And we dealt with quotients in exponential form. So recall, how did I deal with quotients here? This was actually 1 over r e to the, so it was theta minus, so theta sub 1 minus theta sub 2. So this is e to the minus I theta. Right, so this is e to the minus I theta here. Okay. So we have a quick and slick version for finding inverse of complex number in terms of exponential form. But this automatically tells me something important here, right? I don't care about what's happening here. For the argument's sake, all I care about is what's happening up here. But then what's the difference between the angle here and here? Well, there's this minus sign. And so it turns out that from this directly, the argument of z, let me rewrite this because I ran out of room. The argument of z inverse is actually minus the argument of z. And so knowing this fact here, this is the argument of z sub 1 minus the argument of z sub 2. So these are two important formulas for computing these things. Okay. All right, and so how can I use this sort of computation when I am tasked with, say, something like this? So find the principal argument, arg z, where z is, say, minus 2 over 1 plus square root of 3i. Okay. So how can I find principal argument here? Well, I can use these formulas for just the argument and then try to find the principal argument from that. So then I note that from this second formula here, argz is, since z itself is a quotient of minus 2 divided by 1 plus square root of 3i, this is arg of minus 2 minus arg of 1 plus square root of 3i. Okay. So then let's think for a second here. Well, here, finding principal value for, so finding arg of minus 2, I know what that is, that's pi, right? Because minus 2 is on the negative x-axis, so principal value is taken to be pi, not minus pi. Okay. And the principal argument for 1 plus root 3i is, let's think about this for a second. So 1 plus root 3i. So remember here, tan theta is y over x. So this is square root of 3 over 1. What theta is going to satisfy that? Pi over 3 is going to work, right? So pi over 3 is going to work. Okay. So then these are principal arguments for these. Okay. Which means that one possible value in argz has possible value. So it has some value that is just pi minus pi over 3, which is 2 pi over 3. Right? That's just one value. I'm not implying here that it only has one value. So it has 2 pi over 3 is in argument of z. But this is between minus pi and pi. So this actually must be the principal argument. Okay. So let me go over that again, right? This is one potential value in the argument for z. The other values, of course, would be integer multiples of 2 pi. Okay, so once we found this value, once you find any value in argz, you can get all the others by adding integer multiples of 2 pi. Right? And so we found a value, 2 pi over 3, but we didn't have to do anything there to put it between minus pi and pi. All right. So you might ask yourself, like, what could have went wrong here? Like, what if when you did this, right, when you did like whatever algebra that you needed to do in order to compute this, the value you get is something that's not between minus pi and pi? Well, you just add whatever multiple of 2 pi you need to put it between minus pi and pi, and that value would be your principal argument. Okay, so that's how that goes. Okay. All right. So, questions about that? I didn't see any in chat. All right. And so everything we've been doing has kind of been building to this discussion that's about to happen now and for tomorrow, which is going to round out basically the rest of what we're doing in this first big section, which is talking about roots of complex numbers. So so this is our main goal. So what is the deal? When I say roots of complex numbers, I mean roots in the nth root sense. Okay, and so The first thing to note is that if I have two complex numbers, z1 and z2, I know what it means if those two complex numbers are equal in terms of where they sit in the plane. But let's see what it means for if they're both in polar form, right? So if I have two complex numbers in polar form, okay, so there's my two complex numbers. What does it mean if they're equal? Okay. So for rectangular form, it's very obvious. It just means the real and imaginary parts line up, right? The real and imaginary parts are equal. Or thought of as an ordered pair, it would mean that both the x and y slots are equal. Okay. This is a little different for polar form, and of course the reason why it's different can be easily explained in picture. As we mentioned before, there's some ambiguity here, right? If you have, say, even just a single circle of some radius, we'll say R1 here, right? So if here's my circle of radius R1, then Z1 is some point around this circle. But if I notice that even if Z1 is this point, right? Okay, just R1, 0. Then as I'm moving around the circle, I can go around it any number of times, and every time I pass through that point, I'm technically at the same point, even though my angular value is different. Okay, and so what does it mean if two complex numbers that are non-zero, so we're not going to even consider that possibility, what does it mean if they're equal? So z sub 1 and z sub 2 are equal if and only if. So in this course, typically I will abbreviate this as either a double-headed arrow like this, or I will use the abbreviation IFF, if and only if, to say that this implication is going in both directions. It's basically can be treated like a definition. So z sub 1 and z sub 2 are equal if and only if r sub 1 and r sub 2 are equal. That totally makes sense, because if you think about this as specifying a circle, right, then the radii of the circle have to be the same, or else the complex numbers are on different circles. They're further, one's further out from the origin than the other, so on. And theta sub 1 is not necessarily equal to theta sub 2, of course. Theta sub 1 is equal to theta sub 2 plus some integer multiple of 2 pi, right, where k is some integer. Okay. And so, of course, what this tells you is that when you have any sort of interest in solving an equation involving complex numbers, and you want to invoke exponential form in some way, you have to consider this fact that they're equal if and only if this is true. So you could get many values here of theta showing up in some of these expressions. Okay, and so what is the idea? The main idea is we want to use this in conjunction with the identity that z to the n is equal to r to the n e to the I in theta to find nth roots of a complex number. Okay. And here is where the differences between real and complex analysis start to shine. One of the unfortunate, you might be able to say, facts about the reals is that if I were to ask you to compute fourth roots of a real number, right, First of all, you're going to automatically say, well, okay, fourth roots of negative numbers, that's not going to exist. Those aren't real. So we automatically have to discount things like that. But even if I were to ask you, what are the four roots, what are the fourth roots of 1, right? You just say, well, 1, right? 1 is the only fourth root of 1. There's no others. Now, if you've thought about it in terms of like a polynomial thing, you might say, okay, well, 1 is a fourth root of 1 and it has multiplicity 4. So counting with multiplicity, this root is, there's enough of these. There's 4 of them. But the really nice thing about complex numbers is that every complex number is going to have so every non-zero complex number is going to have nth roots. Okay. And so, and this is a fact we're going to see over and over again in this course, that the big difference here is that for the complex numbers, you have something called the fundamental theorem of algebra, which basically says that complex, so if you're doing algebra involving polynomials in the complex numbers, you get all the roots. Okay, you get all the roots. All those polynomials fully factor into linear factors. So that's something that doesn't happen in the reals very clearly, but it's something that does happen for the complex numbers, and it's really, really nice. Okay, and so kind of the first application, or the first place you would notice that, is just in trying to find nth roots of complex numbers. So that's what we're going to do. Rather than start writing the formulas for these things and going through finding them, I'll leave that. I'll start that tomorrow, since I only have a couple minutes left. And yeah, we will finish. If you look at the textbook, we have there's like a first big chapter, chapter 1, or whatever, that has like 11 sections in it. So we will totally have finished chapter 1 by tomorrow. So next week we will start with kind of the beginning of the meat of the course, which is dealing with, or the introduction of analytic functions, and talking about functions of a complex variable, which is the main object of study in this course. All right. So that's the plan. I will post the homework today, later. I'll let you know when I do. There will be an Elms announcement. It will be due sometime over the weekend. You'll have plenty of time to do it. And it will cover most of Chapter 1. It will cover almost every section of Chapter 1, because we will have finished Chapter 1 entirely by tomorrow. So you will be able to do it, having seen everything that you need to see for it by then. So anyway, that's the deal. So I will see you all tomorrow. I'm going to have an additional office hour tomorrow afternoon. I'm aiming for, like, so that it doesn't overlap with your tutoring hour, I'm aiming for maybe like 2 p.m. But I'll let you know about that. So just be watching Elms, and I will send you the link for that. So anyway, that's the deal. So I will see you all tomorrow.